Uh, Hi, yes, my name is Yu, and I'm a spring cohort from Tsinghua University. So I work with Wenrui and Phil here on planet formation. So today I want to introduce you a multi-scale view of circumplanetary disk around giant planets from our simulations. But what you see on the right is the image of a protoplanetary disk taken by ARMA, the large millimeters to millimeter array. And the color here represents the dust thermal emission in the disk. You can see there is a small dusty blob pop up in the cavity of the disk, and that is the topic of the day, the circumplanetary disk around a forming giant. So before we go into detail of it, let's first try to put the image into the context here. So we know planets are formed in protoplanetary disks. And one of the most exciting things over the last decade is that where ARMA, we are able to directly see the disk. Like shown here, all these are actually the dust emission from protoplanetary disk with potentially forming planets. So surprisingly, all these disks, they are not smooth at all. So you see all these rings and gaps features. And as long as people are aware of this rich ring and gap feature in the disk, people start to wonder, okay, what carves it? And the most attractive idea would be baby planets carve the ring and gaps. So imagine you put a giant planet into the disk. It will gradually clear up a gap at its orbit by pushing material away from it, as well as accreting some of them. And so, for example, in the case of HL tau, the famous disk where we see many rings and gaps, so people think the solution would be we can put 3 planets into it, run your best hydro simulations, and you can produce a synthetic image very similar to the observation. So this idea is great. But it remains as a hypothesis until we could actually find a forming planet inside the gap. So that is the point. We are being lucky here that we have this special system, PDS-70, that people identify to creating giant planet inside the bit cavity, PDS-70B and C. So this is a composite image include both the dust emission, scatter light, and the H alpha emission, and all of them point to the two blobs near the planet position. So, more excitingly, if we zoom in near the planet C position, we see these dusty blobs, and this is exciting because that is the accretion disk around C. The thing is exciting because it has been long proposed in theory that when giant planets accrete, it will form these, due to the angular moment conservation, the material will gather around it and form a disk. People usually call it a circumplanetary disk. Now studying circumplanetary become important because you see it connects our protoplanetary disk to the planet. So if you want to understand, for example, the mass accretion rate to the planet, then you need to study how material is transported from PPD, from CPD. And also, circumplanetary disks are the promising site for satellite formation. For example, in our solar system, Jupiter has 4 moons, the Galilean moons, and you can see they are actually almost in a coplanar configuration. People think that strongly suggests that these moons are formed in a disk-like environment rather than random collision. Last but not least, although we see many rings and gaps from ARMA, PDS-70 is the only system we unambiguously confirm it has forming giants. So why only PDS-70? What's the observability of circumplanetary disk. To answer all these questions, we need to go one step further beyond the previous planet gap opening simulation, that is, to resolve the CPD in the global simulations. But resolving CPD in global simulation is numerically challenging due to the large-scale separation. So our Jupiter is at 5 AU, but the Jupiter radii is like 10,000 times smaller than it. So if you want to, when you include the small scales in hydro simulations, the big problem is that your time step become tiny and become very expensive to run through. So, so here I show you actually the best effort in literature today that we have, and you can see they basically only resolve around the 0.1 Hughes sphere at an angular resolution of 1/5. So, so people not familiar, Hughes sphere regulates the gravitational range of the planet, which I will use the term very often. So basically, you only have 5 cells separating the azimuthal direction at 0.1 Hughes sphere. However, our Jupiter is only 10 to minus 3 Hughes radius, which means we still have 2 magnitudes to go. But simulations are limited by small scale time steps. What can we do? Well, let's play some tricks. So in this problem, we focus on the steady state picture of CPD. So instead of evolving the Navier-Stokes equation at the top rigidly, we can add a scaling factor or anything on the time-dependent part of the equation on the left. And whenever the system evolves into steady state, the left part will vanish, and the equation converge to the previous one. So that's our hope, that whenever we run into a steady state, we get a still consistent solution, but we can choose fx so that it is larger than 1, and that gives you a much larger time step. In this specific system, for example, in CPD, we have a characteristic dynamic time scale, which is a Flatiron frequency. We can choose it so that it scale with the Flatiron frequency, and depending on what factor you play, you can get a speed up to 1,000 or 10,000. So here we choose like 10,000. So this is like we want to skip all these annoying iterations before reach a steady state, and well, for the inner disk, the evolution is slowed down because we scale it. So that's likely something happening in time dilation. So we borrow the name and decide to name it as dilated evolution. Sorry, Mr. Einstein. Okay, simulation setup. So as I mentioned, we want to simulate CPD. So we first need to get a clear gap opened by the planet. That's the first step. We put the planet in the disk, let it evolve, and clear up the surrounding until after like 800 orbit, we get a clear gap. And then we start the mesh refinement near the planet to reach the required resolution to resolve CPD. So our goal of resolution is listed on the right. We want to resolve CPD at Jupiter's surface at angular resolution of 1/16. And that will give you a required level of refinement of 12. So this is why we high resolution simulation. Okay, and here is the movie of our CPD in steady state. The orange line here is the Hughes sphere. Then the following columns each are zoomed in by 10 times. So let me play it. So a clear feature you can see, take from here is that across all scales, the CPD is very dynamic. It's never steady, never smooth, but it actually reaches a quasi-steady state in accretion rate. So before making more points on the CPD structure, I want to convince you that the dilated evolution gives you reasonable results. So we can verify this by running a direct simulation at a lower resolution and compare with it with dilated evolution, like shown in the blue and orange. So you can see their accretion rate agrees, their profiles in density and velocity agrees. Okay, now we can look into the CPD. So over the past, so recently it has been proposed that material delivery to CPD is dominated by this large-scale circulation. So gas is dredging up from the disk, while landed directly near the planet, and that drives you a global outflow in the mid-plan. So in this model, in this idea, we have a global de-accretion disk in the mid-plan of CPD. And this idea is actually motivated by the past CPD simulations where people see this large-scale polar inflow and mid-plan outflow. So to examine this picture, we can pinpoint the infalling meridional flow in our simulation. Actually, so here at each radial and azimuthal location, we pinpoint the infall surface and record its height as shown in the green colors, so which is actually the Z over the aspect ratio of the infall stream. And then on the left, we plot the mass injection rate from the infall. So you can clearly see there is an infalling stream from a higher altitude finally landed on the disk at around 0.2 Hill radius. So after this, we can examine the consequence of infall. So we have an infall, we know it, so how it influences the radial mass flux. So here in this plot, I give you the vertical integrated radial flux, which is actually corresponds to the red cartoons. So differently that here I show you the radial influx from different the theta segment. So from 0 to 30 degree, it is a polar region. From 60 to 90 degree, it is mid-plan. So you can see inside the infall radius, which is around 0.2 Hill radius, you see inside it, there is accretion at all altitude. While outside it, you see at the mid-plan, there's a de-accretion and accretion at the upper layer. So taking all these together, we can construct a picture of CPD. That is meridional flow dredging from the disk, from the protoplanetary disk, hit our CPD at around 0.2 Hill radius rather than right at the planet. And that forms you an accretion disk inside it and a de-accretion disk outside it. Since at the planet vicinity, we don't see any vertical infall, then we conclude the most accretion onto the planet is through the CPD rather than the large-scale circulation. Next, now we have basic picture on the flow morphology of CPD. We want to understand what drives the accretion. And in the disks, accretion results from the loss of angular momentum. And in our case, there are three terms that could transport angular momentum, which is the Reynolds stress, mass accretion, and the tidal torques. So on the left is the local change of angular momentum driven by the three terms. You can see as expected, the mass accretion will bring in angular momentum, while Reynolds stress dominates the angular momentum removal in CPD. So in a general disk context, Reynolds stress dominance in disk usually corresponds to that there should be some spiral shocks in the disk. So we can visualize this by plot the normalized density, and you see, yes, let me play the movie. So you see all these spiral shocks. So some of them are very dynamic, some of them are standing there without with all this perturbation, but inside the very inner region, you also see a vortex. Not much time, but to isolate all the different spirals, we can do some time average. Then actually the standing spiral reveals the static spirals, so which is shown on the left. The static spiral is expected in CPD because we have the tidal force of the star. The tidal force is like a m equal 2 force. Then that should give you also m equal 2 spiral. But we have 3 distinct spirals. And we think that's from the modulation of infall. So to prove this, you can actually resume the simulation, but after removing the disk background. In this way, we actually kill the meridianal flow infall to the CPD, and we see it returns back to the normal tidal spiral case. Yeah, so let me skip some and just bring you up to this plot is that given our very dynamic CPD picture, we can make some prediction on the disk turbulent level, which is quantified by the non-dependent parameter alpha. We get a turbulence level of around 10 to minus 2. But in a normal protoplanetary disk, this level constraint from observation is usually around 10 to minus 4. So we have a much more turbulent environment for satellite formation. And I think I will skip part of it and jump to my take-home message. So we designed and implemented the dilated evolution to speed up hydro simulation. And with it, we identify this global circulation picture as shown in this cartoon. And I'll stop here and welcome to any questions.
All right, questions? Yeah, Andrea?
With this time dilation technique, I'm very confused over this. So let's say, Athena picks the time step. Let's just say you can force Athena to pick the time step at a large radius where the dynamical time is longer. And the discretized form of the equation, so the hydro wants to move everything forward a step, and
Yes.
it does this by multiplying times a delta t.
Yes.
Right?
Yes.
So is the delta t on the inside just bigger than Athena would have chosen it to be?
Yes.
So basically what you're doing is averaging over what maybe would have been 100 time steps using the delta on the top for an individual zone is set by the fluxes at the end of the hydro step, and then you just multiply by a bigger delta t than Athena would want to choose on its own? Is that?
We don't do any average here. So here is that, yes, we choose a larger time step. And so in Athena or in any hydro code, the thing is that when you evolve the system, the fluid element only go one cell, right?
Yes.
So you can imagine in the inner disk, in one large time step, it should go many, many cycles, but we force it to go only one cell. So that's a thing down here. So that means we slow down the evolution of the inner disk. And we believe it doesn't need so much dynamic time scale to reach a steady state. Yeah.
Because the idea is that you're very close to a steady state, so the amount that it would change in one of its local dynamical times would be very small.
Yes.
Okay, okay, thanks.
All right, let's thank you again.